And we said that a mole of anything is equal to Avogadro's number of that thing, which is 6.02 times 10 to the 23. We can take that relationship, that equality, and we can turn it into two conversion factors, right? So that's the same general thing that we did when we saw every other equality before, going back to the metric conversion and all the other unit conversions that we did. Right? The only difference now is that we're throwing in this number that looks a little weird or unusual. It's just a big number, but the idea behind it is the same, right? So we can come up with our two conversion factors, 1 mole for Avogadro's number underneath, or we can flip it to get to the other conversion factor, which means we can use Avogadro's relationship and the mole to convert between moles of something and the number of that thing, right? Whether it's the number of atoms, like we saw the last time, or the number of cookies, for instance, in a mole, we can use that relationship. And that's going to be key as we go forward and looking at some of the other relationships that we're going to see in this chapter. So the other piece of information that we get, not just from what the mole means, but also in terms of the chemical formula, is we also get a ratio of the elements to each other in a formula, right? And last week and the week before, you were able to put these chemical formulas together. So let's start with something really simple, like water, right? H2O. And you actually built water in lab, right? You built the molecule. This is still the same section. Yeah. So in one sec. So in a molecule of water, right, in one water molecule you build this, how many hydrogen atoms do you have? In one molecule of H2O. You have 2, right? Where do you get that from? You just look at the chemical formula. So from the formula, right, this tells us that there are 2 hydrogen atoms in one water molecule. This formula also tells us that there's how many oxygen atoms in one water molecule? 1, right? The subscript for water here, for the oxygen is 1. We don't typically write the 1 in, it's understood. So we have 1 oxygen atom in one water molecule, right? But we said we don't deal with individual molecules in the lab, for instance. We deal with huge amounts, so we can take that idea, that ratio, and we can translate it now to the mole. So we can now say that in 1 mole of H2O, there are 2 moles of hydrogen atoms, right? We just look at the subscripts in the chemical formula. So for every mole of H2O, you have 2 moles of H. We can take this and we can set it up in a way that makes a little bit more sense to us, meaning we can set it up as an equality. We can say that 1 mole of H2O has 2 moles of hydrogen atoms. Right, and again, this is coming straight from the subscripts. You don't have to think too hard about it. Just look at the chemical formula, and you get that mole to mole ratio. That's an equality, which means we can come up with 2 conversion factors. Right, so we have 1 mole of H2O for every 2 moles of hydrogen atoms, and then we can flip that. We get 2 moles of hydrogen atoms for every 1 mole of water. Okay, so these types, the setup that we're using here, this relationship that we're generating, right, we're turning it into a form that should look familiar to you, right? This equality, the general setup should look like old news, and then we take this, and we turn it into our 2 conversion factors, right? We know how to do that. We should know how to do that at this point, right? Where do we get the equality from? That's the new thing, right? And we get that equality from the subscripts in the chemical formula. That's all that the subscripts are going to tell us. It gives us a mole to mole ratio of one thing to another thing. All right, so for water, we also get a ratio of H2O to oxygen, right? So we can say that for every 1 mole of H2O, how many moles of O do we have? 1, right? Because the subscript for O is 1. We have 1 mole of oxygen atoms, right? That's another equality, and then we can turn that into 2 conversion factors as well. Put one over the other, and we flip it. And we get the second conversion factor. All right, so my point here is that when you're given the chemical formula, or if you have to write the chemical formula, the subscripts in that formula give you a ratio or a relationship of the atoms in that formula, and specifically it gives you a mole to mole ratio of each element. In this case for water it's hydrogens and oxygens for every 1 mole of that compound, right? So we looked at, forget aspirin for right now, we looked at H2O for water. We started simple. So let's take a look at how we can use that relationship and do some calculations. All right, so let's say that I had 2.5 moles of H2O. How many moles of hydrogen atoms are present in that sample? So you want to think about it and set it up just like you've done every other mathematical calculation. What are you given? What do you need to get to? All right, so we're given moles of H2O. We need moles of hydrogen. So in other words, we need a relationship between H2O and hydrogen. Right, where do you get that relationship from? The equality, which comes from the chemical formula, right? Which we just generated up here. Right, that's our relationship between the water and the H. We just look at the subscripts. So we're going to use 1 mole of H2O is equal to 2 moles of hydrogen as our equality, and then whatever conversion factor we're going to pull out from that. All right, so then we set it up. We're going to start with what's given. We have 2.5 moles of water. We put that over 1. And then we're going to take our equality and we're going to stick it in here. Right, what's going to tell us what goes on top and what goes underneath? Your units, right? So don't just put the numbers in, include the units. Moles of what, moles of what. Because if you want to cancel out moles of water and end up with moles of hydrogen as your unit, moles of hydrogen should go on top. And moles of H2O has no choice but to go underneath. So we have 2 moles of hydrogen for every 1 mole of H2O. Moles of H2O cancel, and that would give us 5 moles of hydrogen. Right, some of you can probably did that in your head if you're mathematically inclined. right? It's a 2-to-1 ratio. We just multiply the moles of water by 2. But that's where it comes from. It comes from that dimensional analysis or that equality relationship that comes from the chemical formula, right? So the formula gives you that mole-to-mole ratio.
Do we need to pay attention to sig?
You should always pay attention to sig figs, right? So the ratio of the atoms here, is that a measured number or is that exact? The 2 hydrogens, 2 moles of hydrogen for every 1. Those are exact relationships, right? There's not 2.01 moles of hydrogen for every mole of water. And you actually built that, right? You counted how many atoms you have in that molecule of water. So the thing that would drive your sig figs here would be your original number. All right, so the subscripts in the chemical formula, right? They give you a ratio of the moles of one element to the moles of the compound, right? And for whether it's something as simple as water or whether it's any sort of fancy chemical formula you can think of, the subscripts always give you that ratio. Or you just look at whatever the subscript is for that particular element. All right, so we've looked at so far, we've introduced this idea of the mole, and in terms of what it means with respect to the number of atoms or the number of molecules or the number of whatever cookies I think we used as our analogy the last time. In the laboratory, are you able to count out the number of molecules that are there or the number of atoms that are there? Is that practical or feasible, even in the smallest sample of water that you have? Right, that would be impossible, right, to actually count the number of molecules or the number of atoms. What we do measure in the lab, though, are masses of things or volumes of things. So now we need to have a relationship between that concept of the mole and relate it to the amounts that we use in the lab, grams, milliliters, etc. And the way that, or the thing that we're going to use here is something called the molar mass. All right, so molar mass by definition means the mass of what? The mass of how much of something? Mass of 1 mole of that thing. To get the molar mass of your elements, all you need to do is to look at the periodic table. So for example, if you look at carbon, so we just highlighted carbon over here, right? So carbon, as you know now, has a chemical symbol C. What does the 6 on top represent again? Number of protons, which is also called the atomic number, right? That's how the elements are arranged on the periodic table. Yes? And what does this number underneath mean? What is that called? That's the atomic mass or the atomic weight, right? So what that tells you is that one carbon atom has an average mass of 12.01 atomic mass units, right? Which is a really, really, really small unit for a single carbon atom. Do you work with single carbon atoms? Ever? That's impossible. But what that number tells you also is it doesn't just give you the mass, the average mass of one atom, it actually gives you the mass of 1 mole of that particular atom. So we can take that relationship now and just say that 1 mole of carbon atoms is actually equal to that number, 12.01, but now the unit changes to grams. And you can look up the molar masses for any of the elements on the periodic table. You do not have to memorize that, right? You always get a periodic table. So the mass of 1 mole of any single or any element you can think of is found on the periodic table. Is that number underneath? It's usually a decimal number. Right? So 1 mole of carbon atoms would have a mass of 12.01 grams. Right? That's set up as an equality again to show you that you can take that and turn it into what? We get two conversion factors, right? 1 mole of carbon atoms is 12.01 grams of carbon, and then we can flip it. We have 12.01 grams of carbon for every 1 mole of carbon atoms. Which means the molar mass of something, which we get from the periodic table, allows us to convert between grams and moles of something. Right? So now we can make that jump from this idea of the mole to the amounts that we work with in the laboratory, grams, milligrams, etc. The mass of 1 mole of anything, referred to as the molar mass, is always provided to you on the periodic table. Right? So again here, the equality, the way that we set that up, stuff we've seen before, where we get that equality from now is the other new thing. We get it from the periodic table. Right? So whether it is a mole of carbon or whether it is a mole of silver, for instance, 1 mole of silver would have a mass of just under 108 grams. We saw a mole of carbon would have a mass of just over 12 grams. And a mole of sulfur would have a mass of just over 32 grams. Right? So they all contain the same number of atoms. Right? There's Avogadro's number of atoms here, 6.02 times 10 to the 23. A bigger mass than the same number of carbon atoms. Why? Because each atom of silver is heavier than an atom of carbon. So the overall mass then is going to be different, right? But they all contain the same number of atoms if you're talking about 1 mole of anything. So we can use the molar mass to convert between grams and moles. So for example, let's take a look at an example here. So let's say a sample of, and we'll use the one that we just did. Sample of carbon has a mass of 2.50 grams. How many moles of carbon are present? All right, so we'll set it up. We'll approach it the same way that we did every other calculation. What are we given? 2.50 grams of carbon. We need to convert that. We need to calculate how many moles of carbon there are. So we need a relationship between grams and moles, right? And that relationship is the molar mass, which we just looked at for carbon up here on the left side. Right, so we're going to use 1 mole of C equals 12.01 grams of carbon, right? You get that from the periodic table. So our units then are going to guide us when we set this up, right? So we start with what's given, 2.50 grams of carbon, put that over 1, and then we're going to take our equality here, and we'll turn it into the conversion factor that makes sense in terms of the unit. If I want to end up with moles of carbon as my unit, that should go on the bottom or top, if I want to end up with it. It should go on the top, right? Which means the grams of carbon then is going to go underneath, so it cancels out. So I have 12.01 grams of carbon underneath for every 1 mole of C. So the grams of carbon go away, and what I end up doing is dividing 2.5 by 12.01. Okay, and what does that give? Annette? 0.20? 0.20. How many sig figs do you think I should have? 3. 0.208? 0.208 what? What's your unit? Moles of carbon, right? So to get from grams to moles, we use the molar mass. If we were given the moles and we needed to convert that to grams, we also use the molar mass, right? But we just flip the conversion factor depending on the units that we want to cancel out and the units that we want to end up with. So, hopefully what you're seeing, again, I'm going to stress this over and over again, is we're seeing the same stuff we saw back in chapter 1 and 2 with the unit conversions, the dimensional analysis. The only difference now is we're getting those relationships from a different place, right? Whether it's from the chemical formula or whether it's from the periodic table, we can still come up with these equalities that we can manipulate whichever way we need to get the units in the right place so they cancel out and we end up with the unit that we actually need. So we can determine the molar mass of an element simply by looking it up on the periodic table. What about if we had a compound, right? Something that is made up of multiple elements. Can we calculate the molar mass of that? The mass of 1 mole of a compound. Well, let's take a look at water, H2O. So to calculate the molar mass of a compound, you simply add together the individual molar masses for the elements. And we're going to look at the formula to tell us this, right? So and we dissected the chemical formula in the previous section. In water, right, if I have 1 mole of H2O, how many moles of hydrogen do I have? You have 2 moles of hydrogen, right? So 2 moles of H. And in every mole of water, how many moles of O do I have? 1 mole of oxygen, right? From the formula, from the subscripts in the formula. So I know how many moles of each atom I have. Can I convert those moles into grams for each atom, for each element? You can look up their molar masses from the periodic table, right? So if I have 2 moles of, hang on a sec. If I have 2 moles of hydrogen, right, I can look up the molar mass of hydrogen on the periodic table, and I see that every 1 mole of H is 1.008 grams of hydrogen. But I have 2 moles, right? That's why I multiply it by 2. So my moles of H go away, and I get, that's 2.016 grams. And then I also have 1 mole of oxygen. And on the periodic table, if you have yours with you, what's the molar mass of O? 16.00 grams, right? So keep track of your unit. Your moles go away, and we get 16.00 grams. And we just simply add them together. Right? So you sum the individual molar masses for the elements to get the total molar mass of that compound. So that gives 18.02, if we use our sig fig rules, grams. So this tells me then that 1 mole of H2O is equal to 18.02 grams of H2O. Right? That's the molar mass. Say that again? So we just add to get the mole of H2O, we just add together the 2 hydrogens and the oxygen. Yeah. Right, and you can do that, you can calculate the molar mass of any compound. Something as simple as water to something way more complicated, right? So 1 mole of water has how many water molecules again? 1 mole of water has how many water molecules? 6.02 times 10 to the 23. A mole of anything has Avogadro's number of that thing. Right? We wrote out the number on that board the last time, a huge number of things. Now we're saying that mole of water, even though there's a lot of it, it still only has a mass of about 18 grams, right? Which is about that much. Hold your water for a second. Right? It has about that much, 1 mole of H2O. That's about 18 grams. So you can calculate the molar mass of something as simple as water to something that's a little bit sweeter, let's say, like glucose. Okay, so I want you to take a minute, maybe 2 minutes, and I want you to calculate the molar mass of glucose. And I'll give you the individual molar masses. So 1 mole of carbon is 12.01 grams. 1 mole of hydrogen is 1.008 grams of hydrogen. And then 1 mole of oxygen is 16.00 grams. Okay, so calculate the molar mass of glucose. You probably need a calculator for this, right? I don't think, well, maybe you can do it in your head. But you always want to double check with your calculator. So we use the molar masses, right, that I gave you. You can get from the periodic table, together with how many of each of those elements you have in the chemical formula. Right, so we have 6 carbons. So that would give 6 times 12, which is 72.06 grams of carbon. Right, we have 12 H's. Each mole of H is 1.008. Right, so that would give 12.096 grams. And then we have 6 oxygens. Each oxygen is 16. Right, 16 times 6 would be 96 grams of the oxygen. We just simply add those together at the end. All right, and then that should give you how much? 180.16 grams as your molar mass of glucose, right? So we can say then that 1 mole of glucose, C6H12O6, is equal to 180.16 grams. Right, so the molar mass you can calculate just by simply looking up the individual molar masses and multiplying them by how many of each of the elements you have in the chemical formula and summing everything else together at the end. All right, questions so far? Molar masses, moles, setting up the conversion factors or the equalities. Okay, a lot of information is embedded in a chemical formula, but also, as we've seen for a couple of weeks now, a lot of information is also embedded on the periodic table, right? So now we're saying the periodic table gives you the molar mass for each element. You just look it up, right? Right underneath the chemical symbol, you have the molar mass. All right, so let's take a look now at how we can use the molar mass to do some conversions, and they're going to be really similar to what we saw previously. All right, so let's say now that you have a sample of water and you wanted to, you wanted to convert between those two different units. So let's say we had a sample of water has a mass of 155 grams. How many moles of H2O are present? All right, so we'll use some of the numbers we calculated from the couple of the previous questions that we practiced with. Okay, and your approach should be the same, right? What are you given? What do you need? Right, we're given now grams of H2O, and we need moles of H2O. So to get from grams to moles, or from moles to grams, right, that relationship would be our molar mass of H2O. Did we already calculate the molar mass for water? Yeah, we calculated it to be 1 mole of H2O is 18.02 grams of H2O. So we start with what's given, 155 grams of water. We put it over 1, and then we take our equality and we stick it in as our conversion factor with our units driving us, right? That's going to guide us in terms of what goes on top, what goes underneath. If I want to end up with moles, right, then moles has to go on top. So every 1 mole of H2O has a mass of 18.02 grams. So my grams go away. Okay, make sure you keep track of the units. I keep harping on that, and I'll keep doing that because that's your automatic check, right? That tells you that you set it up correctly, as opposed to just putting numbers in and you're not really paying attention to the units. All right, so here we can see the units make sense. We end up with 1 unit, which is moles on top. There's nothing else. That's what we wanted to get to, right? So my setup makes sense. All that's left to do would be to crunch those numbers using your calculator, right? Which should be the easiest part of the problem, using your calculator. So 155 divided by 18.02 would give so how many sig figs in my answer should I have? 3, right? The original number 155. So 8.60. So 3 sig figs moles of water in 155 grams. All right, so we saw with the individual elements, we can use the molar mass for the elements to convert between grams of the element and moles of the element. Now we're using that same idea, the molar mass, to go from grams of a compound to moles of a compound. Question? The only difference now is your compound is made up of multiple elements, multiple atoms, and you have to combine those together to calculate the molar mass of that entire unit. All right, let's scroll down. Okay, so we practiced one of those. Let's jump down to our summary here. Your book has a really good, extremely good, sort of a concept map to help you navigate these conversions. All right, so as you're doing your problems and your homework and the study modules, right, I would encourage you as you're getting more and more practice to actually take this and use it, have it nearby as you're going through the calculations, so you can chart sort of a pathway, right, to get from one point to the other. This only works if you have your stuff organized, right? So when we were going through our practice questions, the first thing that we said was, what are you given? And what do you need to get to? Right, so for example, when you go through your questions, right, and the ones that we did, we were given grams of our compound, grams of water, for instance. We wanted to convert it to moles of that compound. So what we would use to get from where we are and where we need to end up, we would use the molar mass of it. Right, and that's how you use this flow chart. It walks you through each of the steps to get from where you are to where you need to get to. So when you start practicing these problems in the homework and the study modules and also in your textbook, right, remember there are lots of practice problems in your text, you have to take the initiative and practice a lot of them. You can't just do 2 or 3 like we did in class and expect to be good or proficient. You have to practice a lot. Okay, in addition to the homework that you're forced to do, right, you have to do some extra. Using this type of setup, the equalities, the conversion factors that result from the equalities, that's something we saw back in the metric conversions. We're seeing it right now, and we're going to see it again when we start looking at our chemical equations that come after this. All right.